basic thing which come to our mind is, okay, I will try for all the possibilities, which means, what do you mean by well-formed parentheses? It is just an opening and closing bracket, right? Now you know that, okay, you have n pairs of parentheses, so for sure at every place, see, I can imagine one parenthesis as two characters, opening and closing character, that's it. So I know that for every location, I know that, okay, I have to form n pairs of parentheses, which means n pairs, which means my length of all the characters in total will actually be a 2n. Now if my length is a 2n, I know, okay, I'll place a opening or closing, opening or closing, opening or closing. So basically for this, I can place either a opening or closing, opening or closing, opening or closing, opening or closing, and so on and so forth. This is what I am gonna place. So for sure, for every location, every index, I will have two options, either place a opening or a closing, opening or closing. So you can for sure see that I will have two options, and my number of indexes are 2n, because I have n pairs, which means length is 2n. So this is for sure I will generate 2 raised to the power 2n number of possible options, and this is what I'm gonna take. So for sure that, okay, if you generate now, okay, Aryan, if I, let's say, generate all 2 raised to the power 2n parentheses, but if you remember, you have to return all the well-formed parentheses, which means after generating this, you have to check if that specific parentheses out of this, like all of these, you have to check that is that a well-formed parentheses or not, which means I'll give you a normal parentheses like this, I'll give you, of length 2n, where n is equals to 3, which means I had 3 pair parentheses, and I gave you that. Now you have to figure out if it is a well-formed parenthesis or not. So you have to just use a stack, or basically any data structure, so as to figure out if that is a well-formed parenthesis or not. Usually to figure out if the parentheses are well-formed, we use a stack. So we know, okay, again O of n time to iterate on the entire string, or like roughly O of 2n time to iterate on the entire string will be needed to figure out if it's actually a well-formed parentheses or not. So that's another concept which we know that, okay, if we even generate by saying 2 raised to the power 2n parentheses, I will take again O of n extra time to get the parentheses out. And for sure the space will be depending upon how we implement it and all that stuff, but simply, okay, the depth of the recursion will for sure be taken depending upon if we handle the strings which we are making in an easy manner. So mostly it will be a recursion depth and also the string space which it might take depending upon how we implement it. But is it the best optimal way to implement it, to generate all the possible parentheses and then checking it? Maybe not. Why to even generate all the possible parentheses? As you can see that, okay, why we are trying to generate all the possible parentheses and then doing and then making a check that, okay, if it's correct or not. Why not at the first place generate only the correct parentheses, and that will reduce our time a lot. Although not in numbers you might see, but it will be reduced a lot, which means in the very beginning when you had a string as empty, you will have two options, either you can place a opening or you can place a closing. Now by the above way, like which we saw above, we will try for all the possibilities, which means we will try for placing a closing also and an opening also. But it is obvious that at the first location you will only place an opening bracket, but you will see that if I know, okay, I'll place only an opening bracket and I will discard the closing bracket, so all of this entire tree which was about to get formed will actually not be iterated on. So it's roughly that, okay, half of your ways are actually like gone, like you don't have to go on to them. So it's reducing a complexity by half, but again, it's not exactly half. It actually be reduced by quite a lot number, and we will see that entire proof of that complexity also, which makes this problem actually tricky. That because, okay, you can simply implement recursion, maybe backtrack, but again, I'll show you that why recursion, why backtrack. But ultimately the interviewer will ask you, can you please let me know the time complexity of this? And mostly people will just revolve around this as the time complexity, but this is not. It is much lesser than this, because this is the complexity of brute force. And we might think in general, okay, we will just let the upper limit know, and that's a brute force, but it's much lesser than this. So now we will see that the time, if we only choose to travel on the ones which are actually helpful for us, then the time will actually be 4 raised to the power n by root n. as the time for us, but we will see entire thing. But it's just that, okay, now we know that, okay, we will try only for the valid states. So I know one thing, I'll try only for the valid states, which means, okay, I know my n equal to 3, which means I have 3 pairs. So I know one thing for sure, I have 3 opening brackets, I have 3 closing brackets. Now I just have to place these 3 opening and 3 closing brackets onto my entire string. So now what can be an illogical way to place? The most illogical way to place a character, a bracket, or I should say a bracket, will be just if I just place a closing bracket without even having an opening bracket, which means, okay, as you can see, I started my string off. I just use the same example. I started my string off and I placed a closing bracket. That's the most illogical way. You don't even have an opening bracket corresponding to that. So placing a closing bracket without having an opening bracket corresponding to that is the most illogical way to actually place it. So you can see, okay, I have an opening, okay, closing, opening, a closing, but a closing bracket without having a corresponding opening bracket is most illogical thing. Now, how to actually know it's the illogical? Okay, by eyes we can see it's illogical, but how to actually know? It can be shown by saying, okay, we can keep track of number of closing brackets. Okay, right now my number of closing brackets are 3. Number of opening brackets are 3. I just make sure, okay, number of opening brackets remaining, number of closing brackets remaining, which means how many brackets I can place around after this. So at this location, number of opening brackets, let's say it is not placed. Number of opening brackets are 3, number of closing brackets are 3. Now for sure, if we have an opening bracket any day whatsoever, I can place an opening bracket. I can place an opening bracket anytime I want. Anytime I want. So one thing is I can place my opening bracket anytime I want. It's just that, okay, I should be having an opening bracket. If I have, I can place it. That is one condition, that, okay, I will place an opening bracket anytime provided I have the opening bracket. And then if I place, okay, my opening bracket count will reduce by 1. My closing bracket will count remain same because I did not use my opening bracket, sorry, my closing bracket. And for sure, if I am placing a closing opening bracket after my existing string, which let's say existing string is S, then for sure my opening bracket will come in picture after this. No worries, I'll properly dry run this, no worries. It's just understand, okay, how the things can work. Now what about the closing bracket? Here we saw that we were placing a closing bracket, but I know, okay, placing a closing bracket provided I don't have an opening bracket, or basically my opening bracket remaining count is less, is illogical. So I know one thing, okay, if my closing remaining, if it is more than my opening remaining, then only I should actually place my closing bracket, which means my opening remaining is less, which means I have open bracket I have used more previously. If opening remaining is less, which means I have used open bracket more previously, and now I should actually place my closing bracket. So I maintain the closing remaining number of brackets and opening remaining number of brackets only when my closing remaining number of brackets are actually more, which indicates that more than the opening remaining brackets. And opening remaining brackets, if they are less, indicates that I have used more number of opening brackets previously. Then I can just, and again, for this opening brackets remaining, here are 1, closing brackets remaining, again here are 1, equal, again not equal. If it is more, closing bracket remaining are more than the opening bracket remaining, only then I should place a closing bracket. So I know, okay, first condition which I have to make sure to not put an invalid answer, or basically an if condition, just will make sure that, okay, my closing remaining brackets should be more than my opening remaining brackets. And at the same way as we saw that, okay, if I should actually be having an opening bracket, right? So same way I should actually be having a closing bracket to actually place a closing bracket. And ultimately I'll just say, okay, my opening brackets will remain same because I was placing a closing bracket at the end of the day, and closing -1, which means, okay, I use one of the closing brackets, and for sure I'll place my closing brackets as a next character in my string, existing string S. So this is the two operations which I can do, either place a closing bracket or place a opening bracket, and that's what I'm gonna perform. So let's have a glance of how the dry run would look like. So for sure, in the very beginning you have empty string. As you remember, in the chart also you had an empty string. Now let's imagine I had my 3 opening and 3 closing brackets. So 3 opening and 3 closing brackets. Now at the first place I said that I can anytime place an opening bracket, so I just used one of the opening brackets. Remaining opening brackets are 2. Remaining closing brackets are 3 because I never use a closing bracket, and as you can see I used one opening bracket, so my opening brackets remaining are like opening brackets here are 1. Now you remembered, I will not go here because I will not place a closing bracket. Why? Because I know, okay, my opening brackets and closing brackets remaining are same, so I should be having more remaining closing brackets to actually place a closing bracket. So I will not place this closing bracket even at the first place. With this, my entire tree actually went away. Now coming on this, okay, again, at any day, if you have an opening bracket, you can simply place the opening bracket. So I know, okay, I have opening bracket remaining, I can simply place that opening bracket. One more, remaining will be simply 1. But here you saw, okay, my closing brackets remaining are more than the opening brackets remaining, which indicate that, okay, I have opening brackets more used than closing brackets. So I can now use a closing bracket also. So now I can simply use a closing bracket. And as you can see, my closing bracket count reduced. Now simply, as you can see, if I had my opening bracket, I can simply use this. I use another opening bracket, my opening bracket count reduced to 0. And now here also my closing bracket count, if it's actually, for sure it's actually more than the opening brackets, I can also place a closing bracket. And again, by this fact, my closing bracket count will reduce to 1. Now again, I'll here also I can simply have and use my opening bracket. Okay, I can simply use an opening bracket. As you can see, I can use an opening bracket. Here you will see I will not, because I will not put a closing bracket. Why not? Because I know one thing for sure, that it is right now same. So equal number of count of opening and closing bracket have been used. I should be having more opening brackets used, then only I should be actually able to place a closing bracket. So I will not go entirely on this part of the tree. And the same way it will keep on going. Now here for sure I cannot place any more opening bracket because my opening brackets have actually finished. So this will actually not go in on this side. It will keep on trying all these remaining values. So now you know generally that what will happen with this specific diagram, that okay, my base case will look like if my entire string is exhausted, which means I have reached all the opening brackets, I have consumed all the opening brackets, I have consumed all the closing brackets, then I know, okay, this is one valid string which I can push in my answer. Let's name the result, because you remembered what maqsad nahi bolna hai. Our aim was that we have to generate all combinations of well-formed parentheses. All, as you can see, one this, and one this. So I have to form all valid parentheses. So ultimately what we saw that, okay, as soon as we have generated, we can just push back that string in a final answer and simply return from there. Else in the actual recursive case, because you saw it's just a simple recursion. In a simple recursive case, we saw that, okay, if open is more than 0, then okay, I can simply start the solve function. I'll reduce my open count by 1, my close count will remain as it is, and in the existing string, which is, let's say it was an empty, because you saw, okay, empty string, I'm adding a opening bracket, adding a opening, adding a closing bracket. So it said, okay, in the existing string, which is this string S, I'm doing a S plus opening bracket, S plus closing bracket. This is, I'm just adding a character in the existing string itself. Okay, I simply add the character in the existing string itself. And for sure, you remember in the closing bracket, I need to have, okay, for sure, I should be having a closing bracket, and else, like one more condition is that the close bracket count should be exactly more than the opening bracket count. Then I can use the closing bracket, and then I can actually simply do a place a closing bracket. Thus you can see it's a simple recursion which we're gonna apply. Now if I just write the same thing in the code itself, so you will see that the base case looks exactly same what we saw, and the same case written in the code itself in the form of a code. That's it. Exact same case we have seen in the handwriting above. And for sure the simple our main function will look like that. This is the vector of string which I have to return to my answer. So I will just have this vector of string. I know that I have initially n opening and n closing brackets, and this is the vector of string which I will pass, and this is the initial string which I will pass off, and I keep on adding my opening and closing brackets. Now comes the time complexity of this. So as we remembered previously that, okay, this kind of recursion, again the proof of this we will see, but this kind of recursion in which I am just generating all the parentheses, it will go on to 4 raised to the power n upon n root n number of states. Again, its number of states will actually be 4 raised to the power n upon n root n. We will prove this, no worries at all. But just right now remember this. We will prove this in divide and conquer using Catalan number or Catalan formula. But right now, just if you remember this, that okay, for this, these are number of states. These are number of states which it can go through. Okay, 1, 2, 3, like number of possible states it can go through. In the end, in the super end, like number of possible, like valid, go for these many number of times it can go to. But this is not the only thing. Okay, we can know, okay, this is the complexity for this, but there is also some portion of time used in this specific code. What is that code? Again, in an interview, if you are not remembering that, you can just let the interview know, okay, it is 2 raised to power 2n, roughly the time complexity, which you can also see it is 4 raised to power n. But because of this optimization which you have done, which is the if conditions, you have reduced it by the root n time. You have reduced by the root n time, and there is n factor because you are going on to all these states. Again, this is for just you to remember. Proof will be derived by the Catalan formula. We will see that in the divide and conquer approach. Now we saw, okay, this is the entire number of states it can go through, like for the recursion. But the main time in the recursion, one code of recursion will actually be taken, that okay, O of n time will actually be used in the ultimate end of that state to go push back. So because entire string of length 2n will be pushed back to a result which will take O of 2n time for sure. And also, as you remember that in C++, this is the operation which will take an O of n extra time, O of n extra time. How Aryan? Because you saw, if I have a string ABC and then I do a plus operation, let's say add a D, then what it will do is it will return the entire string ABC and then add a D. This is a, let's say if the size of this string is n, so this is a O of n operation. This addition is a O of n operation, which most people don't know even, but yeah, it is. So now you can just easily see, okay, this is the O of n operation. That's great. So for sure, if you just go and look back at the exact same string, so you saw, okay, this, if this is the entire depth, let's say the entire depth of this entire recursion tree, let's take this depth as O of n. Let's take this depth as O of n. So you saw that the string is being built. A new string is being built every time. This is a new string. This is a new string being built. This is a new string being built. And it will keep on being building. So basically at every level, okay, at n, I know I have n levels. At every level, I am building a string at max. It can be at max of length n. When I say length n, I mean actually length 2n, but yeah, roughly, because we don't have a constant number here. So let's imagine, okay, it's length n. And again, that is length of n minus 1, that's the length of n minus 2. But yeah, roughly imagine, okay, length n for every of those levels. And again, Aryan, what about other levels? We are just storing the memory, right? So when it will come back, so this entire thing will be gone. It come back. So now n, like length will actually be used. So for sure, we know one thing, that we have n levels of our recursion and each level will take O of n memory. So we know, okay, we have n levels and each level will take O of n memory. That is the memory which is being used by the string, and this will be actually used by the states, number of states in a recursion. Again, these are many rough stuffs, not exact. These are not the exact stuff, which means you will not have O of n space used by all the levels. First level will have just one space, next will have 2, next will have 3, and so on and so forth. So it's a rough estimation of the time complexity which we have, and that's what is actually okay for the interview. So we saw that, okay, that this will take O of n time for these states. So O of n into 4 raised to power n upon n root n. And this is actually taking O of n square time because of all the levels of recursion, and then again the number of states for the specific optimized approach, which will be 4 raised to power n upon n root n. So ultimately the complexity of this would come out to be 4 raised to power n, root n into 4 raised to power n, which is actually less than what we saw via simple recursion technique, which we saw earlier. That, okay, simple brute force, but still that simple brute force, we imagine that multiple things will not happen there. Still, it is roughly same. What's the benefit of that? We did entire thing if else condition, rather just simply try and make all the possible strings and just have a check. That is the only reason why we choose to do this. It is because we know that number of states will actually be less, which means like how the recursion goes, it will go on to lesser number of points, and that's what gonna derive our solution. So what I can do instead is, I was earlier using a recursion, now I will use backtracking. That is the difference between recursion and backtracking, which means I use the same string, right? I use the same string. I'll use, okay, exactly, I'm not copying the string, I'm not adding a new character to the copy of the string, I'm using the same string. I know I will go on to left, so I know, okay, on this string I'll simply add an opening bracket. As you can see, on this existing string I simply add an opening bracket. Now it will go again, the same string will be going down. When it will be coming up, I know I have to remove the character which I added. This character which I added, I'll remove it and then give it back, because I am not making a new copy. Earlier what was happening, okay, opening, closing. So earlier a new copy was made, opening, closing, opening, and then a new copy, opening, closing. Like this was happening earlier. But now I am saying I will use the exact same string, opening, closing. I'll simply make an opening, but I know it is the exact same string. So for sure here also it would have been changed because it's a exact same string. When I'm moving back, I know, okay, I am going back. So he should go back to its original state. It means whatsoever I added, I should remove that. So I'll simply remove so here also from here it will remove. Now he can actually go on the right side and simply add the other character which was closing. So opening, closing, simply add a closing. And then from here also when he will go back, simply remove it. Okay, simply remove it. Okay, simply remove it. Then I'll simply, again, after evaluating, simply remove it. Cool. And then when he will go back to its parent, so basically it is just that the same string is being used. So here you saw, okay, I just added a character, opening bracket, remove the character, the opening bracket, and then here I added the character, closing bracket. And then for sure when he will come back, he will also remove the character, closing bracket. And that's the simple backtracking, that okay, I just backtrack to my original value. A simple code change which we will do, we will pass the string now by address, because now we are using the same string, we are not taking any copy of the string. This will exactly remain same, because for sure as soon as I get the answer, I will have to push the new answer in my final string, which is the result. Now the change which will come in is this, that earlier I was doing a str plus opening bracket. Now I know that things are passed by address, so I can change the existing string. And the best part about this is I can simply push the new character in the string, which is an O1 operation. So I just took the existing string str, I just pushed the character opening bracket in my SDR, and then I just pass that. But when this entire thing is done, when the entire left part is done, when it is coming back, so the coming back function we write after the recursive call. This coming back thing, I have to make sure, okay, I should remove the added character which I added. So the character which I added was this opening. I'll remove this character. And the same way I'll do it for closing. I'll simply add a closing. I'll pass that closing. I'll simply remove that closing while coming back. So now you saw that, okay, this O of n into first power n, this will this will for sure be there because of this O of n, which will happen for the states. But this thing which was happening, O of n square into first power n upon n root n, this will not happen, because now it is reduced to O of 1 operation, which is the great optimization which we had. And thus a time complexity will actually ultimately be first power n upon root n. That is the total. Again, this is the total number of valid states of our recursion, backtracking, whatsoever you want to say. That is the total number of valid states. And this is derived by using Catalan formula, which you will see now. But yeah, space is for sure O of n because of the recursive stack space which we have. And there is no string space which is being taken because I'm using the string in memory. That is only one string, and that's being modified internally at every time. Now comes the entire part revolved around, okay, we saw the brute force, we saw the recursive, we saw, okay, the improvised one was actually the backtracking one, we saw the improvisation in the time complexity. But how is that number derived? Although in the interview, if you simply say that a 2 raised power 2 raised power n, a 2 raised power 2n, then also it's actually good. Okay, interview will not say much about anything because he also might not be knowing it. It's actually way too much high stuff to know. But yeah, just for your general knowledge. So basically we saw that number of valid parentheses which we could form is 4 raised power n upon n root n, which is the number of valid states. which we could have. Now it is for the length of 2n strings. So if we just represent that, how it's gonna happen is that I can simply say, okay, if I know I have 3 opening brackets and 3 closing brackets, so I can just say one thing, okay, give me, see, place no opening bracket and then place, okay, and yeah, make sure to place opening closing and then no opening bracket and 2 closing brackets, like 2 pair. Here I'll say no pair, 2 pair, 1 pair, 1 pair, 2 pair, 1 pair, and then this is actually constant, opening and closing, opening and closing, opening and closing. So you will see you are actually forming all the possible pairs. So with this no pair, it is inviolate. Okay, with this 2 pairs, I know these 2 pairs can form all these 2 valid combinations. With this 1 pair, it is just opening closing. With this 2 pair, it is all valid combinations. It's again no pair, it is again 1 pair. And again, if I add these, so I'll simply form all these possible pairs for all these. Now this is the answer for f of 3, which means 3 pairs. If I write the same thing for n pairs, I can write the same thing as Cn multi, and this is again the same thing which I wrote here. I can write the same thing as Fn as f of 0 into f of n minus 1 multiplied by f of n minus 1, same f1 f of n minus 2, which is similar to a Catalan number formula. And same the way I represent the same number as C0 into Cn minus 1, C1 into Cn minus 2. Again, that's a similar kind of formula which we could have looked at if we would have known that, okay, Catalan general formula would look like this. Again, this is not a part of your interview and the interview will not ask this, it's just for your knowledge. So now if we just generalize this formula which we saw here, it actually be nth Catalan number will actually give you the number of ways to form the valid combination of n pairs of parentheses, which is actually nothing but first power n. Again, this is a very long proof. You can just write on Wikipedia nth Catalan number. There's a proof which will come in. For the folks who are interested, just get this known. But for the interviewer, of basically to actually impress the interviewer, just know that number of valid states for your answer will be first power n upon n root n. And you know that, okay, for pushing the answer, you will have a n. So ultimately, your time complexity will actually become a first power n upon root n. While many many candidates would be saying it is n into first power n, because they will feel like, okay, this is for result and this is for the recursion, or basically backtracking. And for recursion, they might say n square. But yeah, now you know that you are actually having the best possible answer, which is first power n upon n upon root n, as the time complexity of the entire generating all the valid parentheses. And that's it. Now you know the entire, like from brute force to actually using recursion, which is then optimizing that using backtracking and then ultimately getting the final most optimal answer. Cool. Thanks so much. Goodbye. Take care. Bye bye.